So today we have generally in front of the break. We will talk about subgroups as monoids via the geometry of the graph.
Thank you. Okay, so I'd like to begin by thanking the organizer for the invitation to give a talk. I'd also like to thank my two hosts. I'm visiting David Eastdown and James East. So James East works at Western Sydney University in Parramatta. So what do I want to talk about? So let me give you some idea of the structure of my talk. I want to talk about a current research project I have, which is kind of, I had a little thanks for down at the bottom here. So this is something that started autumn last year and is running for 5 years. I kind of just want to talk about one recent result with Mark Kambites, which is kind of one result within this bigger research project. And what I want to do is I'm going to start by explaining an old problem, maybe like 100-year-old problem, which is still open, which is one of these nice problems that's very easy to state, but seemingly difficult to answer. So that'll be where I'll start. And that's one of the problems that motivates a lot of the work that we're doing, including the result I want to tell you about in this talk. So that's the first bit. Then I'll kind of try to give you a big picture about what this research project's about. And then I want to tell you about the classical result of Higman, which is a result about groups. I'll talk about weird things that are not groups, and then there'll be a whole chunk where I just talk about groups. I mean, I'm doing my best not to assume almost anything for this talk, but I'm kind of hopeful that people might have seen the definition of a group as in undergraduate mathematics, and that's an okay assumption to make. I don't know, I'm just not. So there'll be like first half of the talk, then will be, I'll tell you this classical result about groups, which some of you may have seen and some of you may have not. And then in the second half, I'll explain what these things, inverse monoids are, which are slightly stranger objects, which you might not have seen. So I'll say what they are. I'll say what we proved about them, which has echoes of this classical result of Higman's, has a similar kind of sound to it. And then in any remaining time I have after that, I'll try to explain some of the methods used in the proof. I'm not going to give you the proof, but I want to kind of say, well, what's the kind of ideas that we use for a proof like that? And that's where this geometry of Cayley graphs things come in. Okay, so I'll kind of mention with some examples how this geometry of Cayley graphs is used to prove this result. And it's also nice to mention because lots of things you want to prove about inverse monoids use the same idea. It's like a general kind of way of thinking about them. Okay, I'm just about to tell you what a monoid is, and then I can adapt that slightly and tell you what a group is. Okay, so although I'm probably going to define it in terms of groups, but anyway, so what I want to talk about is something more general than a group, which is something called a monoid. And so here you have an algebraic object, you have an operation, a binary operation, so a way of multiplying things together. It needs to be associative, and you need to have an identity element. And the difference with groups is we no longer insist that elements have inverses. We don't care if they have inverses. And the kind of example to have in mind, something more concrete maybe than what I have on the slide here, I mean, this is concrete, this is different, would be take n by n matrices over a field under a composition of matrices. But take all the matrices. You don't care if they're invertible or not. And not all matrices are invertible, so that's a monoid, it's not a group on the multiplication. Okay, so keep that example in mind as a concrete example of a monoid. But what I want to talk about are monoids and then later groups and inverse monoids defined in terms of presentation, so defined using generators and relations. Okay, and this is a combinatorial thing. It's a combinatorial way of defining a monoid using a finite. I mean, I'm typically interested in when they're finite, so using a finite amount of information. And I'll focus on this example for now. Okay, so you should view this. What is this saying? As so in general, we'll have a monoid. It'll be generated by some symbols, and it'll have some defining relations which specify some things that are true between these generators, right? And what this is meant to denote is the freest monoid that's generated by these generators subject to these relations. Freest means you just have these restrictions and no additional restrictions. And what it means in practice is you have words, which are strings of letters over these generators. And you have a notion of equivalence of words, where two words are equivalent, and you can transform one into the other using the defining relation. Okay, so the elements of monoid are actually equivalence classes of words. Fine. So let's have a look at the little example where here I just have a single defining here. So we've got A and B are the generators, and the relation is BA, BA, BA. And I'm going to ask you some questions. This is my interactive slide. So, question: in this monoid, is ABAA equal to AABA? What it means is, starting with this guy, can you transform it into this guy in a finite number of steps? And the moves that you're allowed to do is everywhere you see BABA, you can replace it by A as a subword. You can replace it by A. Or everywhere you see an A, you can inflate it and replace it by B, A, B, A. That makes sense? And you go in either direction as you go along the steps. So question, okay, well, we can get people to put up their hands. Do you think you can get from this to this using this rule in several steps? So who thinks yes? Who thinks no? Who doesn't know? I guess that's everybody else. Okay, so maybe it's a bit unfair because we've not seen an example yet. So the answer on this is yes. And hopefully this line will help clarify this idea of applying relation. Okay, so we start with the thing on the left, A, B, A, A. I spot this A. I'm allowed to replace that by B, A, B, A. So now I've got A, B, A still, that's the same as before. And this A has now been swapped by a B, A, B, A. And now I've got A, B, A, B, A, B, A. But then inside there, I spot another B, A, B, A. This one, B, A, B, A, this one. There's a few B, A, B, A. There's this one in particular. I can now squash this down to an A. I can replace this by an A, if I like, using this relation again. And now I've got A, B, A. Happy with that? So these two elements represent the same element as mono, they're equal. Okay? Okay. Question 2. Is ABAA equal to AAAB? So I chose this because looks a bit similar to this, right? In this one, the question was, can we kind of move the B along? Move it along. And now I'm asking, can you move it along further? Can we move it along to the very right? And the people who think no, is that because you've seen so many exam questions that you know for sure I wouldn't do 2 yeses in a row here? Or can you see a reason? So does someone have an argument? Why can't I get from this to this? Can't get rid of the B on the right. Exactly. Yeah. So, or yeah, exactly. Or the other way around, which is the exact same statement. If you start with this expression, so you notice this relation, this word ends in an A and this word ends in an A. So if you apply it to a word that ends in an A, the result will also end in an A. And so no matter how many times you apply it, you're never going to suddenly end up with a word that ends in a B. So you can transform this. Notice 2 different sort of games happening there. When you want to show they are equal, you just need to come up with you need to come up with a sequence of applications of relations that shows they're equal. When you want to show they're not equal, it feels a little bit like what we were doing there. It's kind of, you have to come up with some reason why you can't do it. But there it feels like you're having to do something a bit more creative, maybe. I don't know. Okay, third example. What about ABBAA equals AABBA? So this time we're trying, a bit like this, where we try to move the B to the right, we're trying to move some B's to the right, but now we've got paradigm. You can do stuff. You can start doing this sort of thing to try and push it to the right. Maybe, I don't know, try to do some similar things. So who thinks that they're equal? Who thinks that they're different? Okay, and who doesn't know? Okay, maybe I'll leave that with you. So if you get really bored and the rest of you both, you can take a piece of paper and try to solve it. So it is answerable, but I don't know, like there's a very reasonably straightforward argument for this one. I don't know, there may be one, for example, I don't know. I don't know a similarly kind of, if you're trying to show they're not equal, similarly straightforward, oh, well, one ends in an A and the other ends in a B, is not, you know, they both end in A, so that previous argument's not quite working. Maybe there's something similar, but it's as far as more thought, right? Okay, so you've now been introduced to a problem, you've never seen it before, which is very old, maybe 100 years old, maybe less. I'm not quite sure when it was originally written down. So what we're doing there is called the word problem, right? The word problem. Given 2 words, are they equal? And a question you could ask is, okay, we don't want to spend our lives doing this. Given an example like this, we'd like to write a computer program which takes as input any 2 words and then says yes or no, they're equal, yes or no, right? And stops in finite time, it tells you yes or no. And if there is an algorithm for a given example, then you say that that monoid has decidable word problem. Okay? This one does, by the way. There's an algorithm. I'm not telling you what it is, but there is one. But the general question is open. So it's not known whether the word problem is decidable for monoids with a single rule. With a single rule. If you allow finitely many rules, then there are classical results that say you can have undecidable word problem. But with a single rule, is not known. With no rules at all, of course, this problem is trivial because you can't apply any relations. So being equal means who equals words. There's nothing to prove. By the way, the result for groups, there's an analog of this for groups, the same game. And word problem for one relation groups is known to be decided. So there's a classical result of Magnus from the 1930s that proves that. This one's been hanging around for ages. And this is one of the kind of motivating problems. I'm not going to specifically talk about this problem, but I'll explain how the stuff later on relates to this one. Okay. So don't worry about this slide too much. This is just to say, try to give some big picture. I haven't defined what inverse monoid is, but we've defined what monoids are. So so the thing I'm interested in doing is investigating problems like this problem, this word problem for one relation monoids, and other similar kind of algorithmic problems in algebra. So this is something that kind of lives between algebra and logic and theoretical computer sciences somehow. And what we do is we look at monoids that we just saw defined by generators and relations, but also groups defined by generators and relations, and also a class that lives between monoids and groups, which I'll define later, called inverse monoids. And you can also define those using generators. And each of these areas kind of, so you might call this combinatorial algebra, or in group theory, they now tend to call this geometric group theory, studying things defined by generators and relations. Each of these has its own kind of flavor. So when you're doing monoids, it feels combinatorial and has links with things like theory of string writing systems and so on. Over here in the world of groups, it feels more geometric. And there's lots of ideas from topology and this kind of thing. This can all be expressed in terms of fundamental groups of certain spaces and this kind of thing. And then inverse monoids, I want to try to convince you is a nice class that lives between monoids and groups, where you have a little bit of the best of kind of both worlds. You have some of this kind of combinatorial string writing stuff coming over, but you also have, you can do things that feel a little bit more like geometric group theory that you can't do for general monoids. And what's nice, although I won't be able to tell you too many of these, is there's quite a number of nice theorems that kind of are reduction results that say, if you're interested in solving something over here, like the word problem for one relation monoids, then you can instead investigate some problem over here, or maybe some problem over here. And if you can solve that problem, it will give you information about the problem you started with, maybe even solve it. So there are a bunch of arrows pointing between these various classes, and the argument is that we should be developing all three of these theories at the same time, and then exploring these connections. Okay, that's the big picture. Okay, so now I'm going to talk about groups, and I'm going to talk just about groups for a bit. So just as for monoids, so I've now written mon because I'm going to talk about monoids, groups, and inverse monoids. And so what a presentation is depends on like what kind of object it is you're looking at. So mon here is the same as what we had before, but mon means monoid presentation. And this is a monoid presentation for the free group of rank 2. It has 4 generators, A inverse, B inverse. And it has these rules which say A inverse is the inverse of A and B inverse is the inverse of B and nothing else. So this is the freest group generated by A and B, right? But written as a monoid presentation. It can be proved that given, if you want to solve the word problem, so this game you were playing on the other slide, how would you do it in the free group? Well, there's an easy solution in the free group where you take your favorite word, and what you do is you cancel. So wherever you see anything next to its inverse, you cancel. So B inverse, B, and then this A and A inverse come next to each other, you cancel. And you keep canceling and canceling until you get what's called a reduced word, where no symbol's next to its inverse. And then you can prove that these reduced words are unique representatives of the elements in the free group. So to test whether two things are equal, you can reduce them and then check whether those words are graphically equal to each other. Okay, so that's the free group. You can solve the word problem there into the free group of rank 2. And because it's going to come up later, you can draw a nice picture of the free group called the Cayley graph. You can do this for any finitely generated group, where the vertices in this picture are the elements of the free group. And the edges correspond to multiplication by generator. So this is the identity element in the middle. This is A, this is AB, this is ABA, and so on. And you can see this picture keeps track of cancellations, right? So if we do A inverse, B inverse, it's the identity element, which is exactly what it should be. So this is called the Cayley graph of the free group with respect to these generators. You can define more generally a Cayley graph of the group like this. It's like the finite generators. Happy with that? Okay. So then the analog of monoid presentations for groups is group presentations, and you write them like this. So we're going to write group generated by A with these defining relations. And what's the difference? Well, now we're allowed to use the symbols A and A inverse, even if I haven't written the inverse anywhere. We have equality of words, and what are we allowed to do? Given 2 words, we can either apply the relations wherever we like to transform one word into another, or we can apply any of the things that are true in a group for free, and we don't explicitly write those as relations. Okay, so whenever you see AA inverse, you can cancel it, and you can insert AA inverse wherever you like. So you write a group presentation for a group, it looks like this: A and B and no reason. It's maybe a more sensible thing to do. If you're a group theorist, you know that A inverse and B inverse exist, and you know that A inverse is 1 and so on. So there are certain relations you get for free. Another example, free abelian group Z cross Z, so direct product of Z with itself. This is a presentation. It says A and B commute. Okay. So we say a group's finitely presented if it admits a presentation defined by a presentation where the generators are finite and the set of defining relations is finite. And now we get on to Higman's question, Higman's result. So here's a natural question. So suppose we want to study finitely presented groups. Then it's natural to say, well, what are their subgroups? What are the subgroups of finitely presented groups? But we don't want to look at all of them because that's crazy. So what we'll say instead is, what are the finitely generated subgroups of finitely presented groups? That's the question we could ask. Now, okay, it might have been the case that finite presentability is preserved passing down, right? It might have been that finitely generated subgroups of finitely presented groups are finitely presented, but they're not. So it's not true that they're all finitely presented. This is not the first example, but it's just to say that there are examples that look quite innocuous. So you can take the direct product of two copies of the free group of rank 2, and inside there you can find something that's finitely generated that is finitely presented. But already in kind of innocuous looking examples, this weird behavior can happen. So they're not going to all be finitely presented. So then you might well ask, well, maybe every finitely generated group embeds in a finitely presented one. Maybe that's possible. But this second bullet point says that can't be the case either, because there's too many of them. So there are uncountably many pairwise non-isomorphic two-generated groups. And the point is that there's only countably many, up to isomorphism, countably many finitely presented groups. And then if you look at finitely generated subgroups, you're still only getting countably many things, right? And so there's too many of these things for them to all arise inside finitely presented. That's all I'm saying. So the answer is not everything, and the answer is not just finitely presented things. And to some extent, you might expect, well, maybe this is one of those questions that doesn't have a nice answer. Maybe this is just some bizarre class of groups, the finitely generated groups, the finitely presented groups. But Higman proved that it has a nice answer, has a precise answer. And for that, I have a couple of definitions, and then I'll state Higman's result. And this is where you get into something like getting a bit into logic and a bit into kind of theoretical computer science. Here, when I say algorithm, I'm not going to define Turing machines and stuff like that in this talk. So for algorithm, you just want to imagine your favorite programming language. You sit down, you try to write a computer program to do something. And it will be equivalent, right, to what I'm saying here. So we're interested in sets of words, right? So sets of words over some finite alphabet. And I want to define two notions. I'm using kind of slightly non-standard terminology, but I'm going to define two notions. And this is one thing that could be true. It could be that there's an algorithm for this set of words which takes any word as input. And if it's in the set, the algorithm eventually stops and says, yes, it's in the set. But otherwise, it runs forever. Okay? And in that case, we would say that the set of words is computably enumerable. It's called recursively enumerable as well. Yeah. And it's more standard to call it recursively enumerable. Right? So this is kind of, if it's in, it stops and says, yes, it's in. If it's not in, you might run the algorithm for a week or 2 weeks and it hasn't stopped and you don't know. Maybe you run it another week and it will stop and say yes, maybe not. And another property you might have is that the set of words is computable. Now, if it's computable, that means that there's an algorithm that takes any word as input and in a finite amount of time will stop and will either say yes, it's in the set, or no, it's not in the set. Okay, but it will stop in a finite number of time and it'll tell you yes or no. Now, the interesting thing, so you might think at the beginning of this kind of thing, when you start thinking about this stuff, that the interesting fact is that there are sets of words that are not computable. You might think, oh, that's interesting, there are sets of words that are not computable. But that fact in itself is not that interesting because there's lots of sets of words, right? So if you take A to be a set of size 2 and you consider all of the possible sets of words, then there's uncountably many sets and there's only countably many algorithms. So the fact that there are sets that are not computable is somehow not surprising. It's not surprising that there are sets that are not computable. But it is interesting that these two, it's not obvious on the surface that these two notions are different, but it is a fact that there are sets of words which are computably enumerable, for which this is true, but they're not computable. So this can be true without this being true. Okay. Happy for me to move on? And yes, you can change those words to recursive or recursively presented, and it's the same thing. Okay, so a recursive presentation for a finitely generated group is a presentation on a finite number of generators, such that the set of defining relators is computably enumerable. So when you have a group, you can write all of your relations in the form W equals 1. Because if you have U equals V, you can just write UV inverse equals 1. So you can think of your relations as just a set of words, right? The set of left-hand sides of these groups. And these guys, they include finitely presented groups, but they also include those that are not finitely presented, but such that the set of defining relations is computably enumerable. So that means that there's an algorithm which, given a word, will eventually tell you whether it's in the set of defining relations, but if it's not, it will run forever. Another way of thinking about this computably enumerable, another way of expressing it, is there's an algorithm which will write out the set of relations, and eventually it will write out exactly that set, and eventually every relation will appear. And you have to let it run forever. Okay, and what Higman proved is that these things, these recursively presented groups, are exactly the finitely generated subgroups of finitely presented. Okay, so finitely generated subgroup of a finitely presented group is precisely one that can be recursively presented. This is one of those theorems where I think one direction, there's like one easy direction and one hard direction, in the sense that from the definitions, I don't think it takes much work to show that if you're a finitely generated subgroup of a finitely presented group, then you better be recursively presented. But what you need is the other way around. You need some construction which gives you some recursively presented thing and then comes up with a finitely presented group into which you index. Okay, so that's a nice theorem for the past, which I'm certainly not going to try to prove. It has interesting consequences. You don't need to understand this example, but I put it in any way to say that this is not just some random kind of thing. So I mentioned earlier that there are finitely presented groups with undecidable word problem. I kind of just said this in passing at some point. The original proofs of that will go back a long way, but you can actually prove that by applying Higman's result. The idea is something like the following. This result says some nasty groups can appear as subgroups of finitely presented groups. Think about it that way, right? What do I mean? You can take a group like this, with a presentation like this, which says a certain conjugates of B are equal to certain conjugates of B, and let I vary through some subset of the natural numbers. And then you can choose this subset of the natural numbers to be something that's computably enumerable, but not computable. Okay. I said such sets exist. You do that. And then what does that tell you? Then you can prove basically that these words are equal to each other, even only in this group, even only the I's match up. So if you can solve the word problem in this group, then you can determine membership in this set X. Is the point. Chose an S specifically so you can't determine membership in S, because it's computably enumerable, not computable. You can't determine membership in S if you choose it appropriately. But because it's computably enumerable, you can embed this. It's not finitely presented, but you can embed it in something that's finitely presented. And then that finitely presented thing will also have undecidable word problem because this time. So again, you don't need to understand the full details of that, but basically I'm just saying that this result has nice applications. Like it's one way of seeing why there's finitely presented groups with undecidable word problem, just like that. And don't worry too much about it. It says that suitably nasty groups appear inside finitely presented groups. It's kind of one of those things where as soon as you actually express what S is, you've accidentally got a set that's computable. I mean, it's kind of a bit like, you know what I mean? It's a bit like one of those sorts of things. Yeah. Then the fact that such an S exists, I think, is kind of, it's at the heart of all of this, and it's not. Yeah. Interesting. Okay, so that's stuff about groups. Okay, let's keep going. So let me tell you what an inverse monoid is. So the best place probably to start is down with this picture. So typical example of a group is the symmetric group, right? So in symmetric group, you take some set, maybe 1, 2, 3, and you look at all bijections from that set to itself and the composition, and that gives you a group. Okay. But another thing you can do is you can take a set and you can look at bijections between subsets of that set. So these are partially defined maps, right? So if you want to use group theory notation, this thing is a bijection from the subset 1, 2 to the subset 2, 3 that sends 1 to 2, 2 to 3, 3 is undefined. And you can compose these partial bijections. Well, you can compose them. You just have to be careful about, what it means to compose. So, like when you compose this and this, you only compose where things make sense. So 3 goes to undefined, so that things are over. 1 goes to 2, 2 goes to undefined, so 1 goes to undefined. 2 goes to 3, 3 goes to 1, so 2 goes to. There's a way of composing these things naturally. And these things are not groups, but they have a notion of inverse, a natural notion of inverse, which is each of these is a partial bijection, right? And so there's an obvious partial bijection that goes from this set back to this. So for example, this example, 1 goes to 2, 2 goes to 3. The inverse, inverted commas, sends 2 back to 1 and 3 back to 2. But when you compose these, you don't get the identity element. You get something else, right? When you compose this and this, you get an identity, but it's an identity just on this subset. and it's not defined anywhere else. Okay, so it might map 1 to 1 to 1, 2 to 2, and 3 to undefined. So it's a little like partial identity. Okay, so when you axiomatize this, so this is an example of an inverse monoid. When you axiomatize this, an inverse monoid is a monoid such that for every element, there's a unique element of inverse that doesn't satisfy x inverse equals 1 necessarily, but it satisfies x inverse x equals x, and x inverse x inverse equals x inverse, which in this picture is if you do this, this, and this, it's the same as if you just did this, and the other way around. Okay, and this is your typical example of an inverse monoid, just like this. It plays the same role that the symmetric group does. Yeah, go ahead. Right. So for the inverse, you literally just turn this thing upside down. So you say 1 goes to 2, 2 goes to 3, and you write 2 goes to 1, 3 goes to 2. Which is the opposite of what you said. So this picture is more helpful there, right? You have 2 points, they map somewhere, and then you just map back. Okay. Yeah, formally it's composition of binary relations, I guess, in that sense. But basically, like, maybe this shaded part of the diagram is helpful. What you do is you've got this map in blue and this map in green. You need to figure out what your domain and codomain are. So what you do is you intersect the image of this with the image of this with the domain of this, and provided it's non-empty, this little shaded part, then you can trace the lines back to here and trace the lines forward here, and your composition is the map that maps this to this to this. And if they don't overlap, then it's like the zero line, which would be everything goes in. Okay. It's generic in the same way the symmetric group is for groups. So every inverse monoid embeds. There's an analog of this theorem, the Wagner-Preston theorem. It's a slightly more complicated proof, but every inverse monoid embeds in one of these guys. Can be expressed faithfully as one of these guys. Finite. Every finite in a finite, but not, well, clearly not every infinite in a finite, but it's general. Yeah. I mean, as for groups, right? If you let your symmetric group be massive, then you're okay, right? Because you just let the group act on itself, and then you have such a thing, right? It's just, it can be Sx, where x is something silly. And it's similar here. It's more or less the right regular representation, but it's a little bit more. Okay. Right, this is the most horrible slide. So if you get past this slide, then you're in good shape. So I want to talk about inverse monoid presentations, just like we talked about group presentations and monoid presentations. And just like for group presentations, there was a bunch of relations we got for free. So in groups, you got x inverse equals 1 and x inverse x equals 1, and those were for free, and you didn't write them down. Okay? Or maybe another way of saying it is this: group presentations are about expressing things as homomorphic images of the free group. Monoid presentations, homomorphic images of the free monoid. And here you need a notion of free inverse monoid. And you're expressing things as quotients or as homomorphic images of the free inverse monoid. So you better to look at this half of the picture, first of all. So the free inverse monoid takes letters A, B, A inverse, B inverse. You're allowed to write strings of those. And you need to know when they're equal to each other. Now in a group, you just freely reduce, and that tells you when they're equal to each other. But here the rule for being equal in the free inverse monoid is more complicated. And the rule is this. You can express it down here. Take your word and draw a picture. And what you're drawing here is part of the Cayley graph of the free group that we saw earlier on. And what you do is this word needs to not only know where it goes, but it needs to know where it travels on the way. So you start at a vertex. Imagine this is the identity element in the Cayley graph of the free group that we saw earlier on. And you trace out this word. So this word would say, first of all, we start here. So this is the starting point. You read A inverse, that's this and this. Then you read B inverse B, A inverse A, B inverse. And you record where you started and you record where you finished. Okay, so that's this picture is this word where I record the start, I record the finish, and I record everywhere I visited along the way. And this word gives you the same picture. If I start here and I go B inverse A, B inverse A inverse B, then I get everything in this picture and nothing more. I had started here and I finished. So these are called Munn trees. And the word problem in the free inverse monoid says two words are equal even only if they give you the same Munn tree. Yep. You just care about things visited at least once. Yeah. So yeah, you could go back and forth along this one like a million times, and that's fine as long as you visit the same places. Okay. But notice we're not saying A inverse equals 1, right? It doesn't. Okay. The more complicated way. So what is then this line? What is an inverse monoid presentation? You have generators, you have relations, which are written over A union A inverse. And if you want to know whether two words are equal, then your moves, your allowable moves are, you either apply a relation, or you apply something which you know for free, and the stuff you know for free are these things, right? The stuff in the free inverse monoid. So if you write down these, you try to write down a set of rules which gives you this, you end up with infinitely many rules like this, which you get for free, where X and Y here range of all possible words. So you get this weird thing. The free inverse monoid as a monoid is not finitely presented. That's a kind of, but as an inverse monoid is presented with no relation. Okay, so don't need to memorize this. It's just to say there's infinitely many things that you can do for free, and those are expressible in terms of these. You don't need to remember this, just to explain. So that I'm going to have inverse monoid presentations and just say they're like, that's what they are. They're these things. Okay, suppose you're studying inverse monoid presentations. Then there's a particular case with this unfortunate name is special. There are probably a lot of things, too many things in mathematics called special. So special here just means a presentation where all the relations are of the form something equal to 1. Nothing on top of that, just that. Not every inverse monoid can be presented that way, but if it can, then we call it special. And now I want to link this back to the very beginning. Remember that problem about monoids from the start? So this is inverse monoids. This is not monoids. But Ivanov, Margolis, and Meakin proved that if the word problem is decidable for all one relator inverse monoid, this form, special one, then it would imply that the word problem is decidable for all monoids. This open question from the first slide. And you only need to do it where R is a reduced word. A reduced word in the group theoretic sense, so a word that doesn't have any symbol next to it. All you want to take away from this is that if you can solve this problem, you can solve this problem. And when R is a reduced word, this is still open. When R is a reduced word, is open. This is a possible approach to solving the problem for monoids using inverse monoids. And then why might you think you're happy to try and solve that? Well, for monoids, the special case is solved. There is a lot of information on this slide. So if you go to monoids, open in general, but when you do R equals 1, that is solved. That was solved by Adyan a long time ago. And the way Adyan solves this is by showing that the group of units of this, so the invertible elements of this monoid, together, you take those, there's a group inside this monoid, particular one, the invertible elements, forms a group which is a one-relator group. And then Adyan reduces the word problem for this monoid to its group of units. But the group of units is one related group, and then this classical result of Magnus says you can solve the word problem there. Okay, so this is solved, this is open, but this has been linked to this, which is open. And the hope was, well, let's try to do something similar for these guys, Because Adyan did it via subgroups, he did it via these subgroups. In fact, I defined something on a previous slide that I didn't even say, which is by a right unit, I mean something that you can right multiply and get 1, and a left unit you can left multiply and get 1, and a unit has both of them. So units, something that's genuinely invertible inside the monoid, and they form a subgroup. Okay, so that motivates, we want to try to study the subgroups of finitely presented special inverse monoids, in particular in the one related case, and maybe prove they're one relator, and then do some theorem like this to solve this problem instead. So if we look at the general, if we look at Adyan's result, so Adyan's result was for special one relator. You can also, Mackinnon generalize this. So you can look at monoids defined by special presentation, R1 up to Rk, so this is monoids. And Mackinnon showed that the group of units of this thing, so this group sitting inside, is finitely presented, and it's presented by a presentation with the same number of relations. So this is all very abstract. So here's an example. So what Mackinnon really proved is, if you take a monoid that looks like this, not an inverse monoid, but a monoid, and you've got some relations. Here we've got AB equals 1, ABCD, ABCD, ABCD. Then there's a kind of, let's say, there's a method where you can start spotting things that are invertible. So for example, AB is invertible because AB multiplied on the right by AB is 1, and AB multiplied on the left by AB is 1. So it's invertible. Right? It's its own inverse. So if you multiply by itself, you get 1. And once you know that AB is invertible, you can stare at this and convince yourself that CD is invertible and so on. And you can kind of color in this thing into these kind of pieces, which are called minimal invertible pieces, let's say, is a partition of this thing into pieces that are invertible, and it can't be refined any further. And you can say, well, these AB and CD are invertible, and they satisfy an obvious relation, which is the relation x squared equals 1 and xy, xy, xy. Okay, so if I use capital X for AB and capital Y for CD, they certainly satisfy these two relations. And what Mackinnon's theorem says is that that's actually a presentation for the group of units of this thing. Obvious that those relations are enough, but they are. I haven't told you everything here, but this is the essence of Mackinnon. Okay, so, and notice it preserves the number of relations. Even if Mogulis and Meakin, like 20 years ago, they showed that for inverse monoids, some of this is true. So the group of units of this thing is finitely generated. They proved it's finitely generated. And so that was kind of halfway towards trying to prove a Mackinnon-style theorem. Maybe the group of units of this thing is finitely presented. Okay, maybe there's something similar to what's going on here for monoids, but for inverse monoids. And notice the special case of this in one relator, that would have one relation, and this group would be a one-related group. And so this question hung around for ages. And then relatively recently, with Nick Rushkutz, we showed that this theorem's not true for special inverse monoids. And not only is it not true that the group of units is K-related, and you can find the presentation of K-relators, but it can kind of go wrong more catastrophically. So there are finitely presented special inverse monoids, this group of units is not even finitely presented. So they're all finitely generated, but not necessarily finitely presented. Okay, so it's contrasting with what's happening. And so after we did that work, it opened up a question, which is, well, what are the groups of units of these things? As you vary the presentation. Here we know that they must be finitely generated. And here we know they're not necessarily generated. And this should now remind you stuff from earlier in the talk. Because Higman's situation, different to this, was a situation where there were some groups, the finitely generated subgroups of finitely presented groups, which were finitely generated, but not necessarily finitely presented. And there was a question of what are these groups? What are the groups of units of finitely presented special inverse monoids? That's the question. Remember, special just means that the relations are of the form W equals 1. It's no additional. And so that's what Mark and I worked on. We worked on several things, but this was part of it. And it does have a nice answer. And it's the same groups that come up in Higman's theorem. So the groups of units of finitely presented special inverse monoids are exactly the finitely generated. We know need to be finitely generated, recursively presented. The ones that we defined earlier, the ones with the computably enumerable set of relations. So the good news is I got as far as stating the result. So it's not the analog of Higman's theorem for inverse monoids. It's not that. That's a separate thing. That's another theorem which exists. But it has a spirit, some sort of a spirit of that, right? You have some groups you want to know, and it turns out there are these groups. And just like in Higman's theorem, one direction of this is easy, which is like for general reasons, if you're stuck inside a finitely presented special inverse monoid, if you're a group stuck inside there and you're finitely generated, you're going to be recursively presented. There are general reasons for that. A few lines, so general stuff. The other direction, you need a construction, right? So the other direction, you need to start with something recursively presented, and we come up with some finitely presented special inverse monoid that realizes that as a group of units, right? So it's all about coming up with a construction. And of course, we use Higman's theorem, right? So Higman's theorem says we don't need to worry about recursive stuff. We can just work with finitely generated subgroups of finitely presented groups, which we know are the same thing. So our starting point is, so you could rephrase this as they are the finitely generated subgroups of finitely presented groups. So that's what I just said here. One direction is straightforward, and the other direction requires a construction. For trying to, and that construction is trying to realize weird groups as groups of units of these things. Interesting. So, short question session. Just so I can show you, I mean, I didn't expect to have much time for this next part. So there hasn't been any geometry, right? Not much. There's just been the Cayley graph of the free group. Let me just give you some indication of some technique that we use to prove this result. I'm going to draw some pictures, so you don't need to really remember too much on this slide, but there's a certain graph, S gamma 1, which is, you take the Cayley graph of M, which is defined just as it was for groups. Imagine that now it's like a directed graph, but just imagine how we define Cayley graph of groups. You can do something similar for M, but you only want to look at right invertible things. You restrict just the right invertible thing. So it's a subgraph of the Cayley graph. And it turns out the group of units of this thing, which is the thing we're interested in, is isomorphic to the automorphism group of this graph, where you preserve the label. The label preserving automorphism of some infinite graph. And there's something called Stevens' procedure that tells you how you can build this graph iteratively using two operations called expansions and Stallings folding. So what we want to do is write down examples, construct these graphs, work out what they look like, compute their automorphism groups, and then work out what groups you can get. That's the game. Now I can give you some pictures of that kind of game. A couple of pictures, and then I can stop. Imagine you take this example: A inverse B inverse. And this is what you do. You first of all, you write down a little square with that relation: A inverse B. And then you repeat it everywhere: A inverse B inverse, A inverse B inverse, A inverse B. Everywhere, just in a tree-like thing. So those are called expansions. We've done all our expansions. But what we want is this graph to be deterministic. And it's not at the moment. For example, there's a B coming out and a B coming out. We don't want that. Single B coming out of any vertex and a single, most one B coming out and most one B coming in, and so on. So we can fold this edge onto this edge, and so on and so on. So there's kind of infinitely many of these things. One needs to set this up carefully to check that what I'm saying is well defined and doesn't depend on the order in which you do things, and there is a well-defined limit and all these things. But in this example, I might be able to convince you that when you fold this up, you get this picture. You stopped. And this is now a picture of this S gamma 1. This is the Schützenberger graph of 1 for this example, is this picture. So now if you want to know the group of units of this thing, you take this graph and you consider its automorphisms, but you need to preserve the labels. Now, if you didn't preserve the labels, you maybe have 1, at least you could reflect, right? But since I've got this labeled by A and this labeled by B, I'm kind of stuffed. I can't swap those two guys over because I need to preserve the labels. So in fact, the group of units of this is trivial. And one way of seeing it is by considering the automorphism. More interesting example. If you take this example where you have x, a, b, x equals 1, do the same thing, x, a, b, x, a, b, x everywhere. Next functions. Now I fold this thing up. I think that's the picture from my advert. And you get this thing, which is sufficiently complicated. I'm no longer drawing the symbols, but this has been color-coded. So this is x is this black edge, and then this is a, b, and this is x. Now, if you stare at this for a while, maybe not so obvious from the way I've drawn it, there is some symmetry that preserves the colors of the edges, which is the one that translates this central thing up and down. But when you translate this up, you have to kind of flip this over to that side and flip stuff over to that side because of the way I've drawn it. But you should be able to convince yourself that you can go 1 step up, 2 steps up, 3 steps up, and so on, up and down. And these automorphisms are the whole thing, so they're preserving. And that these are the, in fact, you can also check, these are the only automorphisms. And so the group of units of this is that. And notice this looks a lot like the monoid examples from before because x is clearly right invertible and x is left invertible and AB is left invertible. So you can kind of think about it in those terms. But these two examples we've got both finitely presented groups, right? And so essentially the game is do this, but come up with a more complicated construction which realizes any finitely generated recursively presented group as the automorphism group. You want a graph that is that there. But you use Higman, so you really start with a finitely generated subgroup inside a finitely presented group, and that's your starting point. And so, yeah, that's a picture from the paper. There's a more general construction, which I'm certainly not going to try to explain, but it's in the spirit of what we were doing in those examples, where you start with a finitely generated subgroup of a finitely presented group, and we're able to construct this thing such that when we build the Schützenberger graph, its automorphism group is isomorphic to G, to H, the group we started with, and somehow the picture looks like this. And it's kind of about taking a copy of the Cayley graph of G, identifying a copy of the Cayley graph of H inside, and arranging things so that this set is preserved set-wise by all the automorphisms, so that actually the entire automorphism group, even though there's all this kind of other stuff floating around, turns out to be every automorphism is reduced by an automorphism of gamma H, and conversely, so you end up with the automorphisms of the Cayley graph of H, and therefore you end up with H because you're preserving labels. Okay, but there's lots of details missing here, but that's the kind of idea. Okay, I'll stop there. This one? Yeah. That's an excellent question. Why can't we do this along the black lines? The other black lines, yeah, the black lines are good, but the kind of the green, you're right, the green and the blue, there's kind of too many, right? That's good.
But you also have a translation.
Yeah, it's kind of let's say that when you move this red dot up and down this vertical kind of spine, once you've decided where the red dot's going, then that determines where everyone else goes. If you think about it, because imagine I move the red dot up too, then the way that the nature of this graph is that there's one black arrow coming out of that red dot, so that edge must map there, and there's one coming in, so that edge must map there. The green edge coming in must map to the green edge coming in, and so on. And that this kind of determinism of the graph can things that so it really just comes down to where you send the red dot. Does it make sense? If it wasn't like label preserving, this would all work quite differently. Obviously, clearly, but it's okay.